you all for having us. My name is Adriana.
Samantha, Romy,
Cedar,
Isaac,
Kyle,
Emma,
Eva, Jennifer, Emily, Arushi,
Kaden, Josh.
Kaylin, Olivia.
And we are Rosh Bosh. Today we are here to present to you a solution to antibiotic resistance in the 21st century.
Ever since the discovery of antibiotics in the early 1900s, antibiotics have been instrumental in reducing mortality from bacterial infections. Chronic overuse of antibiotics has led to the evolution of strains of bacteria that are resistant to the medications that are aimed at treating them. If we continue down this path of abusing antibiotics, it is projected that bacterial infections will kill more people than cancer by 2050.
On a molecular level, there are a number of mutations that bacteria may undergo to become resistant, which include altered semi-permeable membranes making the bacterial surface impenetrable by antibiotics, and ATP pumps that will actively push out antibiotics on the surface.
Another mechanism that confers antibiotic resistance is altered shape of the bacteria that prevents antibiotics from attaching to it. Lastly, the bacteria can evolve traits to destroy the antibiotics completely.
Additionally, there are many clinical implications AR has on modern medicine. The first is a decreased effectiveness in treating bacterial infections, and secondly, there are many economic implications, which include increased use of hospital resources and longer stays in hospitals.
In the past, the CDC, the WHO, and FDA have attempted to lower antibiotic prescription rates, promoting healthy lifestyles and creating stricter regulations for antibiotics. However, these have not made significant progress on the antibiotic crisis. The answer might just lie on phage therapy.
This therapy spins off bacteriophages. Bacteriophages are a subset of viruses. They attack specific bacterial cells, inject their DNA using host machinery in order to eradicate them. By using these weapons against specific bacteria, we can target only the bacteria that needs to be killed.
This method of phage therapy involves injecting multiple phages into an infection site. From there, a phage will then inject its own DNA into a bacteria cell, and using host mechanisms will then produce more phages from inside that cell. Bacteriophage lytic enzyme, or lysine, will then break down the cell membrane of the bacterial wall, releasing those phages into the host, the process will then continue. Now, to produce new phages, we use a process known as bred, where phages are bred by genetically altering the DNA of bacteria to produce phages from inside the bacteria cell until the bacteria cell eventually bursts and the phages are produced.
With all these new phages, we can use what we call the serial passage method, in which we take a sample of the infection, we take the bacteria from the infection, we place them in a vial, and then we also take the newly made phages from the bred method and also place them in the vial. Some of the phages will penetrate the membrane of the bacteria that is causing the infection, and the ones that don't will die, leaving us with only phages that are able to treat the specific infection. These phages will go into the infection and they will reproduce as phages do and create tons and tons of new phages that are specific to that infection. We then take these phages and inject them into the infection site, and the phages will go in, do as phages do, and destroy the infection.
We are unable to test phage therapy firsthand, but we can convey its effectiveness and need through 3 different cases. The first 2 cases communicate its effectiveness and prove that it is a valid treatment method. The third case portrays the dire need for phage therapy.
Our first case is a 17-year-old man from France who experienced recurrent skin infections due to a rare genetic disorder after acquiring a multi-drug resistant bacteria. He was eventually cured with phage therapy.
In the second case, phage therapy was successfully used to cure an antibiotic-resistant infection following a lung transplant. This case out of the UK demonstrates the efficiency of phage therapy. Our third case demonstrates the effects of superbugs in the US. In Nevada, a woman died from a superbug that was resistant to 26 different antibiotics.
These cases clearly show that phage therapy is a promising solution and that there is definitely a need for it.
There are a number of reasons why phage therapy can be a possible solution to combat antibiotic resistance. Firstly, because bacteriophages do not affect the useful bacteria in your body system, specifically those in your gut, as bacteriophages are highly specific.
Bacteriophages have low inherited toxicity as they are made up of nucleic acids and proteins. In addition, scientists make use of highly purified methods to prepare phages, which prevents anaphylactic responses to bacterial components.
Bacteriophages can also absorb biofilm, which is a layer of viscous material which protects the bacteria from antibiotics. Thus, bacteriophages can be used against both resistant and non-resistant bacteria.
Autodosing is when phages are capable of increasing in number, especially at the infection site, which means smaller doses are needed. Selecting new phages is also a much quicker process than creating new antibiotics. It takes weeks compared to years.
However, there are limitations to phage therapy. Ever since its discovery in the early 1900s, several concerns have been raised about using phage therapy to combat bacterial infections. One of the concerns is the narrow host range of phages. They are effective against only a few strands of antibiotic-resistant bacteria.
Because of this narrow host range, using phages as a treatment option can be really time consuming, as the doctor first has to identify the particular bacterial strain that has infected the patient and then think of the specific phage that could be used to combat that infection.
Secondly, not all bacteriophages can be considered appropriate for therapy.
For example, if the phages are temperate, they display superinfection immunity, which results in the conversion of phage-sensitive bacteria to phage-insensitive bacteria, which could lead to problems in therapy.
Lastly, there is a possibility of bacteria developing resistance against bacteriophages.
Bacteria can combat phage attack via different mechanisms such as mutations, restriction modification systems, and adaptive immunity. Experimental data has shown that phage-resistant variants occurred in 80% of the studies targeting the intestinal milieu and 50% of the studies using the sepsis model.
Thank you all for listening to our project. Bacteriophage therapy is an innovative solution to antibiotic resistance. Although it has its limitations, we are excited to see the advances in the future solutions to this complex problem. Thank you for your time, and we would be happy to answer any questions.
So, wonderful presentation. I wanted to ask all of you, how many of you have heard of bacteriophages before you got here? More people than I expected. So I've heard of them, and you probably know way more about them than I do. In an entire career in medicine, the subject from medical school on never came up, never came up. And there's an interesting political context to that because there are modes and fashions in all professions and in the sciences. And the mode was antibiotic, kill the bug, kill the bug. There's only one way to kill the bacteria, and that's with a new super better antibiotic. So and it's rather interesting that bacteriophage therapy has been around for about a century. I understand it's been used in Russia, for example. Last night I discovered some of the case reports that you've already described, where it's used in people often who are immunocompromised or have very difficult to treat infections. And one that I could add is a successful treatment of people with prosthetic knee, like total knee replacements, or orthopedic artificial joints. And they can become infected, and the bacterial agent can form a biofilm, which is in your poster, that ordinary antibiotics cannot deal with. The biofilm is protecting the bacteria, but the phages have figured out how to get at them. So it's really, in fact, an exciting area with a lot of potential, and you described it as well as the limitations very nicely.
I have to agree with Michael. This was an excellent presentation. Sorry, Peter. I loved your introduction, and also the fact that all of you spoke, and really some of you must be in theater because I like the way you kind of moved around in a very synchronized manner. So that was very impressive. There's a this is really important because you started off with the background, you went into what the gap in the research is, and that's really important because you're trying to convince people that this idea is filling a particular gap. And then you wrapped it up with, limitations, and then you gave potential solutions. So it's not only that you've thought of what the limitations of this brilliant idea is, but you've also thought of, okay, you know what, this is the first limitation, and when you're writing a peer-reviewed publication, that's exactly what you're going to do, is you're going to present the peer limitations, and then try to say that, why, while these limitations are there, this is the strength of your research. And you really, portrayed that very well. And I also like that the way you presented these 3 case studies or the case reports. That was really well thought out, and it really kind of encapsulated the work, the research. I had sort of 2 questions. So what do you think are the barriers to implementing this?
Yeah, so again, there are definitely significant barriers to this. Phages, when they target bacteria, they only target one specific type of bacteria with a specific type of DNA. So it would be quite difficult if a patient comes in with an illness that we don't know. It would take a while to get the specific phage for that disease. But for common diseases that we often treat with antibiotics that are becoming harder and harder to treat with antibiotics, we can develop phages ahead of time that are specific for these really common diseases. That way, when people come in and they're resistant to antibiotics, we can treat them with phages.
I think we also have to consider the political barriers and kind of for the past 60 years, like what has been brought up, the Soviet Union and past Soviet states have been using phage therapy because of their lack of access to antibiotics. We have to consider how this phage therapy is only really legal right now in 3 countries, which are in Eastern Europe, and we have to consider that. But it is important that there are now 3 experimental phage clinics in the US, and it's becoming more popular again. And I think that the barriers did exist at one point because there was kind of this East-West feud and kind of antibiotics versus phages, but now that those barriers are kind of breaking down, and I think we're going to see a lot more research because of the interest in phage therapy.
That's great. And are you seeing a build-up of this research, like with these political barriers that are being raised?
Yeah, because the places for phage research in the U.S. have only been recently opened up. It's only, like you said, it's only been in the Soviet Union before, and now that it's collapsed, we've seen an increase in phage use, which is really remarkable.
Well, thank you. Excellent presentation.
Can everybody hear me? Yeah, we'll switch microphone. So congratulations. I really like the level of detail you had in your presentation, and it's very obvious that you did extensive research, and that was really great. You didn't get lost in detail, but it was really, you had enough evidence, and I agree, I like the case reports too. That's a nice way of, it was nice to see this interleaved in your presentation. So when antibiotics were invented, probably I don't know, but I imagine that the idea of antibiotic resistance didn't come to mind for quite a while. But now, with hindsight, you wonder if, when you look at a new alternative, would there be a possibility of something like bacteriophage resistance in the future too? And my second question would be, if you now have bacteriophage and use that in patients, could that help actually alleviate the problems with antibiotic resistance? Because bacteria undergo mutations, we don't treat them with antibiotics, so maybe over a certain period of time, certain antibiotics could again become effective. I'm just, just throwing out this idea, and it's not my area of research, but just wanted to hear what you think.
There's actually been research that when you use bacteriophages, the bacteria have to make different mechanisms to adapt to become resistant to those bacteriophages, and that lowers their resistance to the antibiotics. So you can use them in combination to fight off the bacteria, but also if you use them, the bacteria becomes resistant to the phages
but the phages can also become more powerful, so they can build their own weaponry back.
Something else that we had come up with was that when antibiotics were discovered, they were overused and overprescribed by doctors quite often. So with this, we hope that they weren't the phage therapy wasn't overused to the point where there would be a resistance built up very quickly. Because it's a very serious issue because as antibiotics really opened up a lot for combating many bacterial infections, and it'd be really horrible if we went back in time before all of these really serious illnesses weren't able to be treated.
Yeah, I also think it's important to note that phages they're not man-made. They've existed as a virus. So, and as viruses do, they adapt. And so, unlike antibiotics, which are human-made, we can't just force them to adapt. With phages, if they struggle to get into the bacteria, they find a way in over time. So I think it's important to note that. And also, as she said about how we use them in combination, because we can't just inject as many phages as we want, because the phages will, if they destroy too much bacteria, that can lead to sepsis, for example, and we don't want to lead to that. So we only want to inject a certain amount of phages to destroy the bacteria.
Thank you, very interesting.
Yeah, did you come across any information on whether the intestinal biome, that is all those bazillions of bacteria that live in our intestines, have a relationship with bacteriophages? Are the bacteriophages as well in the intestinal microflora?
Sorry, can you repeat the question?
Oh, I just wonder if we were carrying around bacteriophages, because we get along with billions of bacteria that are in our gut. As long as they stay in the gut, we're perfectly happy with them, and they may benefit us in a number of ways. But I wouldn't be surprised if you think of biological phenomena as competition. There may be some synergy that is mutually benefited interactions between two different species, like we may be helping the bacteria and they're helping us in ways we haven't figured out. And competitive relationships, which happen all the time in biology. But I wonder if anybody's looked actually at the gut flora to look for bacteriophages in animal gut or human gut. It's just another thought about maybe these things are here all the time and they're actually being nice to us and keeping that bacterial count about right so everything works well. It's just another intriguing question that your presentation provoked.
Well, of course, the idea of the microbiome is relatively new. However, there isn't much research related or looking at we have seen that pertains specifically to bacteriophages. However, the brief research shows that we won't harm the whole system, not every bacteria, because it's understanding that there can be symbiotic relationships as you stated, and that can be very helpful to the body. But bacteriophages, they only do attack certain family of bacteria, and so even if there is a lack of knowledge between us, it can be seen that it won't totally destroy that whole biome, and that it only destroy the bacteria that is it is being bred to take care of. So.
Yeah. Another area that is important in terms of therapy development is the complexity of the treatment. Since antibiotics often can take the pill, that's very easy and convenient. Whereas phage therapy sounds like, at least in its current state of development, it's much more complicated. And that goes on to who's going to invest, what venture capitalist or big pharma is, or the federal government is going to invest in this potential therapy versus other avenues for investing in research and development.
Like my colleague said, right now we are unable to firsthand do this phage therapy, but with further research, I'm pretty sure we'll be able to understand the extent of phage therapy and the dosage amounts and to what extent each patient needs phage therapy and for which infection they have.
Yeah, and additionally, just like as she kind of was mentioning, just how it's not so prevalent right now. So if more people get out and it's brought, because there's only 3 countries that use it right now. So if it's brought more into the U.S. as it is with the experimental clinics, then it's prevalence will be known more, and then big companies and things will see it and, take note that maybe this is a possible solution to this problem.
Yeah, and it's also important to note that in the United States, which is a very capitalistic country, it's all about money here, and all companies are trying to make money. And as antibiotics become less and less powerful and useful, more and more companies are going to see the use of phages as they have been used in Georgia, for example, for almost 100 years. So if a company can be the first one to develop this new medicine that antibiotics cannot fight, that's magical. That's what people are looking.
And it's also only a matter of time, as we brought up in the third case, the 26 antibiotics, it was also to the extent the superbug that was found in the woman, it was resistant to all available antibiotics in the US. And so it's only a matter of time, seeing that also the WHO predicts that per year after 2050 it's going to kill more than cancer, that one of these companies will take up the research.
Yeah, I think the fact that you brought up that particular case is a really excellent point, that we're seeing the limits of antibiotics, antimicrobial agents as the way to cure all bacterial infections. And it is time to look at other ways, more creative ways. You've done such a nice job of presenting today. I suggest you go down to our neighborhood pharmaceutical company and do your presentation there and see if you can sell them.
I have one last question out of curiosity. What do you think drove the development of bacteriophage therapy in the Soviet Union? They may not have had access to antibiotics. So that suggests that bacteriophages was easier to produce, or which may actually be something positive for what you have in mind, because a country which didn't have maybe the pharmaceutical industry developed to the same level as the US, other countries pursued that strategy which you proposed successfully, maybe requiring less resources. So did you look into that? What drove the development?
In the Soviet Union, there was no access to antibiotics because the United States was not sharing their stuff with the Soviet Union, because they were trying to duel and trying to top each other in every way. And people were getting sick and they had diseases, and they were desperate to find solutions. And so they realized that phages work, and evidently they do. So they started taking it up, and the Soviet Union didn't share it with the U.S., and vice versa. So now that antibiotics are wearing off, we would be using Soviet methods here, and yeah, that's why, because the Soviet Union didn't have access to antibiotics.
All right. Thank you very much, Team Rustock. And next up, I believe we have